9.5 Alternating Series. This section will introduce us to alternating series that contain both positive and negative terms. Let's start by revisiting the harmonic series. Given the harmonic series summation from n equals 1 to infinity of 1 over n, number 1, consider the idea that you wanted to have the signs alternate on each term. What would you need to do to the formula to cause this to happen? I'm sure many of you are thinking what I'm thinking because you've seen these alternating series and you've seen something like this, negative 1 to the n over n. That negative 1 to the n is what makes it change from negative to positive. You could have also said summation n equals 1 to infinity, negative 1 to the n minus 1 over n. That would also give you an alternating series. This first one would be for the first term to be less than 0, and the second one would be for the first term to be greater than 0. Okay, so depending on how you wanted to start that, what you wanted your first term to be, you would use one of those to create that harmonic series. Well, it's not the harmonic series, it's the alternating harmonic series. And for that second one, your S sub 1 would be 1. Your S sub 2 would be 1 minus 1/2. So that would be 1/2. Your S sub 3 would be 1 minus 1/2 plus 1/3. And so that would be 5/6. Your S sub 4 would be 1 minus 1/2 plus 1/3 minus 1/4. And that would add up to 7/12. S sub 5, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 would add up to 47/60. So what they want you to do is they want you to next use the number line below to plot the sum of your new series. So what we're going to do is we're just going to say, okay, well, I'm going to make this from 0 to 1. And I know that halfway in between, I have 1/2. Now, think about where your 5/6 would be. That one is just going to be way up here, 1/6 away from 1. Where would your 7/12 be? Well, 6/12 is 1/2. So 7/12 is going to be just a little bit, a 12th past 1/2. Where would your 47/60 be? So that would be 4.7/6. So it'd be right behind or to the left of your 5/6, because 4.76 comes right before 5/6. So you can think of things like that, but you wanted to know where all these sums were, because what we're going to do is we're going to say, okay, our first sum was 1. So that was our first sum. Our second sum was 1/2. And actually, I want to draw it a little bit differently because I think it will help. If I show it as 1 minus 1/2, I'm going to show it like that. Because you're thinking of, you went to 1 and then you subtracted 1/2 to get that S sub 2. Your third sum was 5/6, so you added 1/2. You subtracted 1, you added 1, you subtracted 1/2, then you added 1/3, and it brought you to 5/6. So that's going to show me going to 5/6 for my S sub 3. My S sub 4 was 7/12. So again, you went to 1, then you subtracted a half, then you added a third, and then you subtracted a fourth. And for that one, I'm going to do it in green. Again, another green. So that's your S sub 4. And then your S sub 5 is your 47/60. So that would be from this point to your 47/60. That's your S sub 5. So you can see you're like plus, then minus, then plus, then minus, then plus, then minus. So by definition, an alternating series is a series whose terms are alternately positive and negative. Alternating series can occur in two ways. Either the odd terms are negative or the even terms are negative. And so alternating series test, we have the summation, alternating series summation from n equals 1 to infinity, -1 to the n times a sub n, and summation n equals 1 to infinity, -1 to the n plus 1 times a to the n converge if the following conditions are met. Every a sub n is positive. Okay, so that's without the plus and minus signs. The limit as n goes to infinity of a sub n is 0. Now think about that alternating series that we just saw, the one for the alternating harmonic series. This one was true. They were all positive. The limit of just a sub n, 1 over n, does go to 0, because if I put infinity down, 1 over infinity is 0. That one became true. And a sub n plus 1 is less than a sub n. Well, these are all less than. Okay, they are all less than. 1/2 is less than 1. 1/3 is less than 1/2. 1/4 is less than 1/3. 1/5 is less than 1/4. Remember, you're not talking about the pluses or the minuses there. So this one is true also. So do you think that your alternating harmonic series converges? That's what you should be asking yourself. So a series converges if its terms alternate in sign, decrease in magnitude, and have a limit of 0. What do you think? We're going to look at it. So word of caution. This does not say that if the limit as n goes to infinity of a sub n does not equal 0, the series diverges by the alternating series test. The alternating series test can only be used to prove convergence. It does not say that if the limit as n goes to infinity of a sub n does not equal 0, then the series diverges by the nth term test for divergence. It would diverge by the nth term test for divergence, not by the alternating series test. Okay? So you can only prove convergence with the alternating series test. You know, if you want to prove divergence, it would have to be by the nth term test for divergence. Okay, that would not be the alternating series test. So, example number 1, determine whether the following series converge or diverge. So we've got part A, summation from n equals 1 to infinity. We've got alternating -1 to the n over n squared. So we've got our alternating sign. We're going to look at what our a sub n is. And I'm just going to look at it as 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, ... Okay? That's my a sub n as a sequence. Does it decrease in magnitude? Yes. It decreases in magnitude. They are getting smaller. So that's one of the things that we have to make sure is happening. So number one, all of my a sub n's are greater than 0. That was the first thing that they said we had to have. Number two, my next term is always smaller than my previous as n goes to infinity. So that one was true. And then I need to take the limit as n goes to infinity of my a sub n. Is it 0? Yes. Therefore, it converges by the alternating series test. So again, did you decide whether your alternating harmonic series converges? I hope you say yes, because the harmonic series does not converge by itself, but the alternating harmonic series does converge. Okay, so part B. Summation from n equals 2 to infinity, negative 1 to the n plus 1 times n squared over n cubed plus 1. So let's just look at the sequence. If we put a 2 in, we're going to have 4 over 9. If we put a 3 in, we're going to have 9 over 28. If we put a 4 in, we're going to have 16 over 65. And then, of course, it would keep going. So number one, all of my values are positive. They're all greater than 0. The second term is always less than or equal to the one before it. Okay, so 9/28, it's actually less than 4/9. 16/65 is less than 9/28. Okay, or I was going to say for all n, but I'm supposed to say as n goes to, sorry about that, as n goes to infinity. And then number 3, we have to take our limit of our a sub n. The limit as n goes to infinity of our n squared over n cubed plus 1. And we know that the n squared and the n cubed is so strong that we can look at it as n squared over n cubed and cancel and get 1 over n. And then when we put infinity in, we do get 0. So therefore, this series converges by the alternating series.